My name is Solon Spiegel, and I'm going to present the user interface for the CoreIC. So before installing the user interface, we need to verify whether all the drivers are in place. So you go into the hardware sound, device manager, and you look for the library libUSB. So, and identify the device. So here is the USB, identify the device. Once you have identified the device and it's properly installed, so you can start the software. So we open the software and you press execute, and you have the user interface. So there are 6 tabs in the user interface. The first is the header, which is used to configure mostly the board functions. So these are the DC mask for individual channels. So it switches on and off the LDOs for the channels 1 to 8. And the 3 external control signals of the IC, switch 1, SW2, and strobe, you can set at a predefined stage. All these options can be unselected, can be set to the default, select all, and you have a lot of flexibility and set all the controls. On this side of the user interface, you have the data file header, whether you want to choose to save your data as parameter data with no header or a touchstone header. The default is touchstone header. The control file header, which saves the control file, whether it gives the possibility to save the control file or not to save it. And the external USB switch configuration, when it is disabled, so I'm not using the external switch configuration. In this case, the network analyzer is connected directly to the CoreIC. And when it's enabled, I'll be configuring the switch configurator, either according to the word I provide. In this case, I have 1111, which configures the individual switches of the switching matrix. So each switch represents an SP4T switch. And you have placed it with the right. So then you pass this word to the switching board and then configure the switching board. Alternatively, we can configure the switching board using this channel selection as we see the next tab. So the next tab is the sweep control, and it's divided into 3 main windows. The hardware control, which controls directly the CoreIC. So we have a default state, which is the channel 2, phase and amplitude step equal 1, and some of other configurations of the CoreIC. The second window is the configuration of the network analyzer. You have configured the network analyzer, which the software passes pre-configuration through the network analyzer. You can read the data, you can calibrate the network analyzer, and you can restore the state which pre-saved into the network analyzer. There is a frequency index which selects which frequency index you want to make your phase and amplitude sweep. So this is the frequency index. It's 156 out of the number of points that has been preset during calibration of the network analyzer. So the output of the run can be an S21 frequency response of phase and amplitude value as function of the control word, or the correction vectors as a function of control word. The last plot here is the run and plot. In this case, it perform the analysis and show the results in these 2 windows over here. And run and display is basically do the same thing, but it's set the output results at the console rather than on the user interface. We can also have a run and quit the simulation. In the bottom, we have 2 options, which is the applies only phase correction if you want to have phase correction to apply to the data, and apply sine and cosine correction, and basically having the full correction applied into the system. You can have both configurations, either phase of sine and cosine, which actually allows you to apply both amplitude and phase correction. So there are some savings settings. So the tab 3 is the configuration, so that every bit and the register is being explicitly defined. So you can configure, for example, the amplitude and the phase word of individual channels. So these are the main configurations. There are some other controls and programming. We're not going to get into details of all this control. Is in the data sheet, and you can go there later. But you have this amplitude and phase control. Another important control is the input stage. You want to set the gain of the input stage, so you can have this gain control. And there is another option, which is also important when you in the user interface in the MOOC cell. When it sets to 0, basically says that I'm going to take the phase and apply to the CoreIC, and I use the internal ROM to deliver the sine and cosine signals to the vector modulator. But when I set to 1, basically it forces me to configure here the sine and cosine values of the CoreIC. So there are both options available, and the default option is 0, where I actually set the phase rather than sine and cosine of the phase. Okay. So you can also set in terms of registers. So you have the different registers used in the CoreIC. You can configure each register individually and then update the values. So the setup window, basically the main configurations, so that you have, first of all, the address, the visa address of the instrument. In this particular case is what is indicated here. The pre-saved instrument state, so that's with the calibration and data, that's position of the markers. You can preset and save the instrument state. So the name of the file is state RS7308C. The PID of the CoreIC board and the switching board. So use the PID to communicate with the microcontroller of the placed in the CoreIC board as 1002, and with the microcontroller of the switching board at 1003. So there is also switch channel select. So, and then you have a configuration for the different switching positions according to channel selection. For example, when you go back to the channel 2A, it's going to take a pre-configured value, for example, pre-configured value, and then each of the position is used to configure one of the SP4T switch present in the switching board. So you have also the set TX or RX modes. One sets the TX, 0 RX. Basically tells the network analyzer to read the S21 rather than S12 file. So that's why you can, instead of exchanging cables, you can set 0 and 1. So basically you tell the network analyzer to read the S12 rather than S21 result. So where the output directory, where all the data is going to be written, and load sweeping vector. So you can also have a possibility to load your sweeping vector rather than using the predefined sweeping vector on the software. And finally, the README page that explains the basic functions of the CoreIC. So the first thing to do before activating and running everything, because if you do run something like here, it's going to tell you an error. It's going to give you an error. Okay, so the first thing to do is to load the NEC to analyzer interface. So I give you a message on the error. When the NEC analyzer is off, it's not connected, or not run the interface, so it's give you an error. So let's first run the interface, and then get the user interface of the NEC to analyzer. Now that we have the user interface of the NEC to analyzer, we need to configure it first for the correct window to be able to interface with the user interface. So there are different options. For example, if I want to configure, and I press configure, I want to really pass these sweep parameters like start frequency, stop frequency. So it's 2 gigahertz start frequency, 6.5 gigahertz stop frequency, number of points, sweep is linear, and the average. So I'm not going to pass the configuration again. Rather, I'm going to use a restore state, which is already restored in the NEC to analyzer. We are not going to do calibration. It takes time to do calibration, and that calibration was done once you connect the eCall in the NEC to analyzer and you press calibration, and it will take care of the calibration. Okay. So now that you have preset the NEC to analyzer, we can go into the configuration interface, and you see the different configurations. So we're talking about the channel 2A. So I've been connected my board at the channel 2A, and we can see, for example, if I turn off the output stage, and you look on the plot here of the S21, so this is the S21 here. If I update the graph, this is going to be a position, and then it's going to be off. So I'm going to restore the position of 96. So then it's coming back to S21 here, and then I'm going to make my sweeps on this configuration. I'm not going to change this, the amplitude value. So I want to do now is go back to the sweep. And the first thing that you want to go back to the sweep is to have some default state. So I go always to default state. And we can initialize the file. So normally, I initialize the file, the first initialization 2 represents the channel 2. If it's channel 3, I normally use 3. So I do initialization, and it updates the both. So here you also see that I'm running now at my frequency index 156. So my result will be determined at the frequency of 5.51 gigahertz. So let's do one small analysis. And first of all, let's get into the data files. Let's go to the data files. And we're going to do again. I'm going to erase all these data files, and let's do some new simulations, some new measurements. So I'm going to do it first, like we're going to do an amplitude sweep. And I want to initialize my amplitude sweep now. Okay, so it's going to take, this word is not important. I'm going to, because this is the value of 96, it's not important since I'm doing an amplitude sweep. It's going to take the values defined in the range 32 to 56 with the number of amplitude steps that I want. So let's see, in this case, I want you to have 16 steps, not to take too much time. And then it's 201 points in the frequency. So then I press save, and then I press run. So let's wait and then go now to the console and see if it's really working. So I see the interactions is proceeding, and we're going to expect the data coming. You can see here at the date. So you see the data file has been created. So, and let's finish the simulations. 50, and it has complete. So you really see here the name of the data file, and it has been complete. So if you open the file, just to expand the file, so it does show the index. So this is the index. So the S parameters in terms of MD format, so this AC format here, the frequency and the S parameters in the real imaginary format. And you can use these files with a different index to bring it back into your ADS environment or Microsoft environment and run your simulations on your measurement files. But you can also, as you go back here, that's a default, and let's put channel 2 and have initialize. Without saving, I can actually basically see my measurements also in my user interface. So I have here the same measurement that I have in the Nectar Analyzer, the S21 file. I also can see on my user interface, and my phase measurement as a function of frequency, which is this plot that I have here. I also have it here. So at this stage, we have been making only an S parameter measurement, and we see that you can download the output file already on comprehensive touchstone format. But you're more interested to do a phase sweep and a specific frequency. So for this, you need to turn the switch other than S21 frequency response into the phase and amplitude value. I'm going to press the save because I want to save the value, and I want to change the phase steps. In this case, I'm going to place 64 phase steps. Okay, so I'm going to run it at this 5.51, 0 to 360 degrees in 64 steps. So let's execute. And then you open the console to monitor if you have the sweep. So we have the sweep started. And it's going to end when it reaches the 364 steps that has been implemented. So one thing that you can see while the system is running is observe the mark. So you see the marks here, either in a polar format or in a rectangular format. So the phase is being swept. So you see the phase is going to be swept. So it can go from minus 80 to plus 80. This is the 360 degrees phase shift here. And you see that you have the switch in the phase, and then it's having the sweep. So you can see the markers here or in this way here. Okay. So let's see how many plots are still missing. So we are in 38. I think soon you're going to finish this. So it's almost in the end. So it's already on 61 interactions, 62, 63, 64, and has completed. And then it actually plots the phase. So what you see here in orange is the ideal phase, a linear sweep. And the blue line here is our actual measurement that we have done. And here we have the amplitude variation of my system. And then in this one here is the best fit on the amplitude variation. So even without calibration, we see that we have already a very good fit to the straight line. So we can also run all the correction vectors, which will take the difference or the error vector between my ideal line and my measurement line. So we can then save. So before doing that, let's inspect the two new files that has been created. So we have the 21. So the first number is the channel number, and 21 is basically the phase without correction. Okay. So we have the vector, which is the phase, and that's the amplitude variation. The amplitude, not the variation. This is the phase and the amplitude. And these 415 are the correction vectors. So you have here my control word applied to the CoreIC. So it's this word here. And that file has been generated as 41 because I have been set the safe control file. If I leave it none, I will not generate the control file. Okay. So let's go now and then switch for the position of correction vectors and apply execute. So we're gonna redo the analysis. So you can see here is already started the simulation. You can see also the net analyzer here. The marker is changing. So it's gonna do this interaction until completes 64 steps. So we are now almost in the end. So it's 62, 63, 64 and finish. So, and then it writes the file 3.1. So this is the channel number 3.1. So let's look at this file. So it's been here. So it's been created a file which shows the arrow, the phase arrows and the amplitude arrows. But you can also see this file in the software. So this is uncalibrated phase arrow and an uncalibrated amplitude arrow. So you can now take this correction arrow vectors and then recalculate your control word and reapply, for example, on phase correction only, the results in the CoreIC. So let's look on this, and then we're gonna do first the phase amplitude value and then the correction value. But now I'm gonna run with apply phase correction. So I wanna apply the corrections and look on the improvements of the linearity of my sweep. And I press execute. So it's gonna read this file and then use this file to calculate and correct the control word. So that starts the interaction, and then let's wait until we finish the interactions. So let's go back. We are now almost finishing this analysis, and it saves now the file 222. So we can expect this file if this file is here. So this is a new file that's being created, the 222, the data file. And you see the linear sweep is almost perfect. So it has been actually able to compensate for the phase errors. Okay. So the last simulation that we do is, okay, we want to see in more details the deviation that we have from the linear behavior, which is the ideal behavior, and the actual measurement result. So you can now apply the correction vectors. You leave this apply phase only correction, and then you press execute and wait for the software to start the sweep. It's going to start, just starting the sweep, and the rest then see the results when it completes. So we are now finishing the analysis. So, and it has been now generated the 32 file, and we can see here basically the phase error over 360 degrees. This is the phase error, and this is the amplitude error of the CoreIC. So let's look at the results. So the results we are showing here. So there are different columns on control words, and the first column that we have in Excel here, this column here, is your actual word that you have been applied to the CoreIC. And consider that when you make the measurement of the phase error, that the phase error includes not only deterministic error, but also quantization noise. So this is an error that that apply word comprises on both sources of errors. Okay, so we wanted to remove at least the quantization noise, especially if you do a frequency phase sweep with very small steps, for example, with the 0.5 degree steps. The quantization noise can be higher than your actual phase step. So we have a second column, which is actually the best fit for the, or the average, you can say that is the average of the actually measurement. So this is the second column, and it's normally the control default word that you're going to apply into the system if you use your input is phase. We can also calculate if you want to set the MOC cell to 1 and apply to the system a sine of the phase and cosine of the phase. So basically, so then you take the second word on the column here. So what you see here are the values in decimal and here in Excel, okay? So the third column represents the value of applied to the CoreIC. If I set the MOC cell equals to 1 here, and in this case, I don't apply directly the phase, but sine and cosine of the phase. So these are the values that you have to apply in CoreIC. So the results are all here. So the results of the switch, we have actually performed the first and then the channel 2 with the 64 steps, an S parameter analysis data, and then a sweep data of the phase and the correction phase with and without phase and the correction errors with and without the phase correction. Okay, so this is the graph that we have. So all the results are being plotted here. It can be displayed once the simulation is completed, but also the data file is also available for post-processing the information. Okay. So this is the main user interface that communicates with the CoreIC board. It demands for this version that we have the same Nectar analyzer that I have used in my configuration, although I have been customized the user interface for Nectar analyzers available at the customer. So there is a customization to be done to interface, to communicate with different types of Nectar analyzer. But most of the functionalities are available here. Okay. So now we're going to look on different user interface that we want to perform rather than a phase and or amplitude strip, but a power strip. So let's look on the same CoreIC now the interface to perform a power strip. For the power strip, I'm going to open another routine. So I'm going to come here, Python, and then select the CBN power strip. Okay. And activate the software. So the main configuration is the same. I'm going to say here about 128, or maybe do 96 in the same level that I had before. Let's leave it here in 96. With this configuration the same, and the main setup is here. Okay. So you have the CoreIC PID, switch PID. So normally the switch PID is not used in the power setup. Okay. The instrument state that I'm going to recover on my net analyzer, let me put it here. Where I want to save the data. The name of the file I'm going to change because I have now done 96. L6 and 5.5 gigahertz. I can update this one. And I want to do a strip between -40 to 0 dB. Okay. So let's look now. And then the first thing, let's restore the state. So it's going to take the state that is previously stored in the instrument and then modify the goal. So we're going to restore the states. So these are the restored states. And then I have been modified my user interface here. For example, like 96, I want to load my settings. Load my settings here. And I'm going to update. When I press the update, it's going to take this value here, 96, basically in my channel, in the channel that have been defined here, and it's going to run all only on that channel. So whatever is defined out on the other channel is going to be reset. Okay, so I'm running on channel A, 2A, so it's set 96. So I'm going to press update. So and this is what I have something here. So these are more like to adjust my graph display, to have my frequency index. So this is 5.8. Let's move a little bit my frequency index. I believe load setting is update. That's 5.5, maybe a little bit more. 55. Load set is update. Okay, 56. Let's put 5.5. Okay, that's fine. 5.4. No, doesn't matter now. Okay, so there I set my frequency index, and we can now see when I do the power sweep. I'm interfacing my power sweep at the board level. So if you have a calibration, I have done the calibration, de-embedded the loss at this particular frequency, you can actually enter the input and output loss, and then you compute the correction at the input and the output in dB. So these are the losses that you can apply in your board. One update. And then here, if you want to create Excel, so that's going to create an Excel immediately. So let's run power sweep. So we're going to apply run power sweep. And the same thing you see here. And start the interaction, -40. And let's look at the network analyzer, for example. It's not changing, the power is small, so there's no effect of compression. So this is the sweep. It's important that we have a network analyzer, and there was a difference from the old network analyzers to the new one. So when the new one, old ones, many of them has a sweep range from -20 to 0. But actually, when it goes above -10, the amplitude and phase starts to change. So you need to make sure that you have, for this type of measurement, especially if you want to characterize AM to AM, AM to PM, a network analyzer that preserves the phase across the sweep. Otherwise, you're going to have to calibrate that phase as well. Okay. So let's start running here, -6. And you see now that the amplitude is already decreasing. You see? So it starts saturating. So you have decreasing the amplitude and finish. And then the output has generated a file. That's a log file, but it has been generated a file on an Excel file. So let's look for this Excel file on the data and the log file. And I think the last one that you have done now is 429. That's this one here, 429, time, date. You can open it. And you said that here, the input power, here the phase is not correct. Maybe we have to just reformat the axis. Let's reset the phase. It's okay. And minus, if we can go in -45. Okay, so this is the phase. But most important is this is the input power, the output power for this particular settings. And this is the AM to AM distortion. And then here is have AM to PM distortion as a function of the input signal. So it can have different settings. And this IC, the maximum power, it takes 10 dBm with this particular version, getting a 1 dB compression about 8 dBm at the IC level, at the maximum setting. So we have not displayed a power sweep is also automated. And if you want to do it many channels, your power sweep, it has to be automated, the setup as well. Okay. So these are the first. So there is another one I will not demonstrate, but there is another one for noise. So you also can perform noise measurement with the spectrum analyzer, and it's also been automated to give you the expected results. Okay. The setup is very similar, but instead of controlling the magnitude analyzer, it's going to control the spectrum analyzer. So basically, that's what I want to present. Present the control interface for the CoreIC, because we understand that the customer is not only sufficient to provide the IC. There are many aspects to be you have to provide to them. You have to provide the correct control words. We understand that isolation is critical. Might be one thing that is calibrated at the lab and might not be the same calibration correction words in the real system because of coupling, the coupling matrix of the antenna that is present. So there are different control words that have to be applied. But in a sense, it does give a possibility for the customers to have the CoreIC, but to have the complete support that enables it to develop a proper system with the high degree of phase accuracy and amplitude accuracy as well. Thank you very much.